Let's talk about something that sounds really simple but can actually cause a huge headache for computers, adding something to the middle of a list. Today, we're going to dive into a really clever, really elegant solution to that exact problem. It's called the linked list.
To get what I mean, let's start with a scene I'm sure you're familiar with. You've got your tickets, you're excited for the movie, and of course, your seat is right in the middle of a totally packed row. Getting there is never easy, is it?
You know the drill. It's this whole chain reaction. Everyone has to stand up, shuffle their feet, there are a bunch of excuse me's, it's a mess. That simple act of just inserting one person forces the entire row to shift. Well, believe it or not, one of the most common ways computers store data runs into this exact same super inefficient problem.
So let's take a look at that rigid structure. In the programming world, it's called an array. A good way to picture it is like a rigid digital bookshelf. And, understanding its limits is really the key to seeing why we needed something better.
Okay, so an array is basically like a bookshelf with fixed slots. Every piece of data, every item, sits right next to its neighbor in one long continuous block of memory. It's perfectly organized, which is actually great. It makes it incredibly fast to find something if you know exactly which slot or which index to look in.
And here's where we hit that same movie theater problem. This bookshelf is rigid, right? So let's say we have our numbers all sorted out. 5, 10, 15, 20. The number 12 obviously needs to go between 10 and 15, but there's no empty space. So what does the computer have to do?
Yep, you guessed it. Just like all those people in the movie row, every single piece of data from the number 15 onwards has to get up and move one spot to the right, just to make a little room for our new number 12.
Now, for a tiny list like this, okay, maybe it's not a huge deal. But imagine an array with 1,000,000 items, shifting almost 1,000,000 things just to add one piece of data. No way. That's incredibly slow and inefficient. Clearly, there's got to be a better way. And of course, there is. This is where our hero for today comes in, the linked list. Instead of that rigid bookshelf, I want you to picture a flexible data chain.
So the fundamental building block of this chain is something called a node. And each node holds two really important things. One, the data itself, the number 5 or whatever. And two, something called a pointer. Now this pointer is the secret sauce. It's basically just an arrow that says, hey, the next link in our chain is over there.
All right, let's actually put one together. Every linked list has to start somewhere, and that starting point is called the head. This is our first link in the chain. Right now, its little pointer is just waiting for instructions. Now, when we add the next piece of data, we create a brand new node, and we just tell the head's pointer to point to it. The really cool thing here is that these nodes don't have to be sitting right next to each other in the computer's memory. They can be scattered all over the place. It's the pointer that connects them and creates the chain. And we just keep doing this until we get to the very end. The final node, which we call the tail, has a special pointer. It points to something called null, which is just a universal sign in programming for stop, the end of the line. Nothing more to see here. Okay, so now we have our two contenders. In one corner, the rigid bookshelf, our array, and in the other, the flexible chain, our linked list. Let's put them head to head and really see what the trade-offs are. This chart really breaks it down nicely. Let's start with memory. Arrays need that one big continuous block, but linked list nodes can be anywhere. This gives linked lists a huge advantage in growth because they can grow or shrink on the fly, no problem. Now, insertion. This is the big one. As we saw, no shifting needed for a linked list. But, and this is a big but, look at access. An array is the undisputed king here. You can jump to any item instantly. The 5th item, the 5,000,000th, doesn't matter. It's immediate. With a linked list, you just can't do that. So it all boils down to what you need your program to do most often. If you're constantly reading data from random spots, an array is going to be your best friend, hands down. But if you're always adding and removing things, think about a music playlist or maybe your browser history, a linked list is going to save you a world of hurt. All right, theory is great, but let's actually see that flexibility in action. We're going right back to our original problem, sticking an element into the middle of a list, but this time we're going to do it the easy way. No shuffling. Okay, here we go. Our list starts with A pointing to B and B pointing to D. We want to squeeze our new node C right in the middle. Watch this. All we do is tell B, hey, stop pointing to D. From now on, you point to this new node C. Then we just tell C, okay, now you point to D. And that's it. The chain is reconnected. We're done.
Did you see that? The original nodes for A, B, and D didn't have to move an inch. We just rerouted the connections. It's the difference between making a whole row of people get up and shuffle and just tapping someone on the shoulder and saying, hey, follow this new person instead. It's so much more efficient.
But remember that trade-off we talked about? Every superpower has a weakness, right? Well, the price you pay for all this amazing flexibility is how you actually find things in the list. This is the other side of the coin. I think the best way to imagine this is like a treasure hunt. You get the first clue, and it doesn't tell you where the treasure is. It just tells you where to find the next clue. And that clue leads you to the next one, and so on, until you finally reach the prize. That is exactly how searching a linked list works. The process is called traversal. If you want to find the 50th item in the list, you have no choice. You have to start at the head, follow the pointer to the second item, then the third, then the fourth, all the way down the chain until you get to number 50. There are no shortcuts, no skipping ahead. So, when you put it all together, what we have are two really powerful tools, and each one has its own clear strengths and weaknesses. This brings us to the final and really the most important idea here. It all comes down to the programmer's choice. So what are the big takeaways? It's pretty simple. Arrays are rigid, but they are built for speed when you need to access data. Linked lists are all about flexibility, perfect for when you're adding or removing stuff all the time. Ultimately, there is no single best data structure. There's only the right tool for the job you're trying to do. And that kind of leaves us with a final thought, one that goes a bit beyond just writing code. In almost any system we design, we face this same fundamental trade-off. Do we build for raw speed and efficiency on a fixed, predictable path, or do we build for adaptability, giving ourselves the freedom to change direction whenever we need to? It's something to think about.